Okay, so today is the first session, and we are going to cover some very specific overview and other things. And this session is going to kind of give you an overview of how the basic of Curio works. We are not talking about anything specific, but in general, how this platform, Curio as a platform functions. Okay, and these sessions are some of these sessions would be extremely technical. So if you get bored, you can let me know, and we can switch the content and maybe get it a little bit more up to your speed. But the idea here is to try to impart as much knowledge as possible. So debugging and anything else is looking through code, and whatever you are interested in doing with Curio is easy for you to do. Okay, so let's get started. And we are going to cover today the Harmony scheduler, which is the core of how Curio functions. It's basically the platform, and everything else is just a task in Curio. And then what a typical Curio architecture in terms of a Curio cluster, what it looks like, and what are different things in it. And then we are going to cover some basics about installations, requirements of running Curio, etc. Okay, so these topics are very important for any new SPs joining the ecosystem, because the working of Curio is quite different from Lotus Miner. And in the initial stages, people feel a little lost, especially they don't know how to check for certain things. If something is not working as they expect, they have no clue where to go and look at it. So let's get started on Harmony Scheduler. Okay, so Harmony Scheduler is kind of like, you can think of it as the brain of Curio, right? This is where all the decisions are happening, no matter what the decision is, right? And Harmony Scheduler kind of consists of two parts. First is Harmony DB, and second one is Harmony task itself, right? So Harmony DB is nothing but a wrapper around a Postgres database. This Postgres database is actually Yugabyte database, right? And we just create a wrapper around it. We call it Harmony DB, and it has certain functionality which are specific to our use cases in Curio. So everything, all the metadata that Curio needs to make any kind of decision, it all lives in this Harmony DB, right? And every task that goes through, whatever its requirements are, or where it is supposed to run, all of these details, you can go and quickly look it up all in Harmony DB. Okay, so Harmony DB is very important, and this also clarifies the requirement that we have in documentation, that you should, at least in production, try to deploy a 3-node Yugabyte DB. So in case one of your node is down, Curio doesn't automatically goes down, right? You still have other 2 nodes keeping everything up and running. And it's very, very important to have high availability for the Postgres backing Harmony DB. Now, anybody who's interested in creating their own version of Harmony DB apart from Yugabyte, they can go and look up this thing in code, and it has certain interfaces. If you can satisfy those, most of the things should work without any issues. Okay, second one is Harmony task. Now we have a database, but how do we express things that we want to do, right? Curio needs to do a lot of things. It needs to do window posts. It needs to do different ceiling steps. It needs to do winning posts. It needs to serve data and a lot of other things, right? So how do we do that? I mean, if you go back and look at Lotus Miner, everything was very convoluted, dependent on each other, and it was running through this weird pipeline where tasks weren't truly parallel. They were actually serial, but they just pretended to be that they were getting executed in parallel. So that's not the case with Curio and Harmony. Here, literally everything that needs to be done can be expressed in a task. Now, task here is a format. I'll describe that later. So this is a certain format that we have. And if you can describe whatever you want Curio to do in this format, Harmony will take care of everything else, right? So let's see what this harmony task is actually, right, in detail. And one of the very important things is so basically it has like 4 or 5 interfaces. Anybody who doesn't understand what interfaces is, it's okay. You don't have to worry too much about it. Think of them as like properties of a certain thing, right? And type detail is one of the most important property. This is where you kind of tell Curio like, hey, this is what my task actually is. It's details, right? This is the name. It's going to need 4 CPUs or 2 CPUs. It's going to need a GPU. It's going to need so-and-so memory. It's going to need so-and-so storage. What kind of storage? Like, does it need to be on ceiling storage? Does it need to be on storage, or what's the size that we need to make the allocation? All of these details, right? So they all live in type details. This is the main thing that tells Harmony what this task is and what it needs and how it's supposed to work. Then another very important one is can accept. Now, you want to have that freedom where certain things are done by certain nodes, right? You don't want everybody doing everything because they might not have the resources. They might not have the correct resources, right? So, or even if they have the correct resources, you just want a specific thing done on a specific node or under a certain specific condition. There are multiple example for this. One of the best use cases is that, let's say you want to generate indexes, right? Now imagine if you have a file sitting on a server A, but you're going to generate indexes on server B. That means you're going to do a remote read. You're going to choke up your network. You're going to read the whole 32 gig file and then process it and then add it to the database, add those indexes to a database. That seems like a lot of wasteful time that we can actually optimize. So that's where can accept comes in. Now we put a condition that, hey, only accept indexing task when I locally have on my storage the unsealed copy of this thing. Now we have a better solution. Now the storage nodes are going to be the one that do indexing locally, which is going to be considerably faster than doing it over the network. Next one is do. Do is actually pretty simple. It's self-descriptive, right? You just basically tell what needs to be done. And when all the conditions meet, like the type details, we check this for the CPU and everything, and Army says, okay, yeah, I have this, all the resources. Let's check can accept. Okay, I can accept the task. What next? Let's do the task. And that's where the actual execution happens. So I hope it makes sense to everybody, and everybody's with me till now. Any questions till this point? Okay, great. Let's move on to the next one, scheduling. So now we have seen how we describe a task, how a task is accepted, and how a task is executed. Now the thing is, who creates these tasks? Who puts these entries in Harmony DB, right? I mean, you're not going to go and do it manually. So that's where scheduling comes in. Now in Curio, till now, we have 3 kind of different scheduling mechanisms. One is polars. Now, polars are used for things which have kind of think of them as very long process, which require different tasks throughout the process. So imagine ceiling pipeline, right? You need to first create an SDR task, then create a 3D task, then 3RC, and blah, blah, blah. A lot of tasks, right? Same goes for Snap pipeline. You have to do like 5-6 tasks for it to actually complete. Now, in case of market, we have a similar requirement. So that's where polars come in. Polars are kind of like, they keep checking the database for certain things, certain tables, and they say, okay, a certain condition is met. Let's say, we have completed the STR task. So now I should create a new task, which is 3D for the sector. And that's what these polars do. So we mostly have polars being used for ceiling pipeline, and one use case is indexing that we're using polar. Now, second one is I am bored. And this one is kind of funny. So the idea was to kind of allow nodes to do certain other things if they're not busy. And the one of the most important part of IAM board is that it is actually used to control the snap pipeline. Snap pipeline does not have a polar. We do not actively manage anything. If any node is free and it doesn't have any task, it's going to go and look at IAM board and it's going to see, okay, IAM board. Let's see if there are any tasks I can create. And it goes and checks them and it does them, creates them, and then it completes them. Okay, so that's how IAM board works. The next one is singleton. Now, these are the things that we want to happen only once across the cluster. So let's say if we want to do something which is cluster-wide, let's say generate an alert, right? We don't want every node to go out there and try to create their own alerts. We kind of want to have a central system where one thing runs and checks everything and goes, oh yeah, so and so things are wrong, or yeah, so and so things are green. Everything is good. You're good to go. So these are singleton tasks. We usually use a reserved singleton for GC, for alerting, and anything which requires cluster-wide impact. Okay, next comes in is execution. So we have created the task, we have figured out what different interfaces are, how they work, and all of that. Now, how do we actually execute these tasks, right? So we kind of create this harmony machine, I would say, that's the correct word. And within that, we check all the things that this particular machine can do. We line it up. Think of them as like getting all the details from task details, task type details, and all of those things, can accept and everything. All the decision-making code is now ready, right? So now we have a very long-running polar, which basically this runs as long as your node is up and running. And every 100 milliseconds, we go and check in database that has anyone created a new task in Harmony task table, which does not have an owner. Okay, we get these tasks and then we check a few things. One of those is, do we have the resources? So we check what kind of resources do we have right now? Do we have enough CPU? Do we have enough memory, GPU, storage? Storage is a very important resource here. We check all of this and we say, okay, I have enough resources right now on my node, so let's do a can accept. And we send the task to can accept. Now can accept checks its own condition. If it fails, it tells it, hey, I can't accept this task, and you'll get a log line saying rejected, task not accepted. Because of can accept denial, right? And you'll see the error or warning, and you can quickly realize, okay, maybe let's go and look at the can accept of this particular task. Let's say we are talking about POREP here. Let's see if there are any conditions, and if any of those conditions are not met by my node, where I expect this node to pick up the task, but it's not picking it up. So that's how you can check those things, right? The can accept denials. And if it passes the can accept, then it goes and actually makes a storage reservation. So imagine if there are 10 different nodes, all want to do STR, and you have the ceiling space, all want to do move storage. Move storage is a very good example of this thing. And now what happens in move storage is you move all the sector files from your temporary storage to your permanent storage, right? From ceiling space to store space. Now the problem is, imagine if you have so many nodes doing it and you are very close to getting your node your storage actually filled up. You don't want all of those nodes to go and try at once and fail, all of them to fail, right? So what we do is we do a storage reservation. It's kind of like think of it as a reservation within the memory, within the database. And we don't keep it like, if let's say you had the reservation, but you failed the task, and next time you try again, you can use the same reservation, or after about 10 minutes, that reservation expires. So that reservation is in place to ensure that nobody goes and tries to mess up with your files while you are in charge of the files. Okay, and once that stage passes, we actually go and call the do interface, which actually does all the tasks. And once the task is complete, it either returns did it complete successfully, true and false, and if not, then what was the error, and that's it. And then once the completion is done, we record whatever the result was in Harmony task history table. So if nothing failed, if everything went good, we store a success, and then we delete the entry from the Harmony task table itself, so nobody else tries this again. And that's it. And if something fails, we simply go and log the failure in the Harmony task history, telling, hey, this so-and-so task failed for so-and-so reason at so-and-so time on so-and-so machine. And then we go and retry this after a certain time. So that's how typically your flow of tasks work in Harmony. Okay, so these are the two most important tables when you're trying to debug why things are not working, why things are not being picked up, or anything else like that, right? These are very important. The first one is Curio Harmony task. Anything that needs to be executed on any machine. And if it is a task, it needs to have an entry here. If it doesn't have an entry in Curio Harmony task, even if there's a ID assigned or anything else in whatever the other the task detail table is, it doesn't matter. It's not going to get executed because the scheduler, the main scheduler, the Harmony scheduler, it goes and picks things from this table. And it doesn't care about the internal details. As you can see, it only cares about what is the ID, and some of the things which are actually more about the administration rather than the task detail itself, right? Then the next one is how many machine. This is each of your node is actually registered. That's a very good question, John. I'll come back to it. So the how many machines is basically you're registering each of your physical nodes here. It's going to take CPU, RAM, GPU, and all of that, and then use these entries from the database to actually track things while after the machine has started, like how much CPU is left, how much is already being occupied, being used by some task, and all of that. So these are very important tables. And this is one of the very first stops in debugging if something is not working from Harmony level. Okay, great. Okay, so this is the end of basics of Harmony scheduler and Harmony system. If you have any questions, please ask them now. I do see some questions in chat. Okay, first one is from John. What was the inspiration for Harmony? I think Magic and Andy are better suited to answer this question because they are the ones who came up with it. It took them a very long time to figure out this platform where, we had to find a platform where it has to be efficient, highly available. It has to work across multiple nodes and, keep things a little bit more like we wanted to abstract things, right? So this platform can basically do anything. And it's not limited to doing tasks that we define in the code somewhere deep down. I don't have a very detailed answer, John, but basically we just wanted to get away from Lotus Miner and create a better scheduler, and the answer was Harmony. Okay, Azhar has a question. How many machines is constantly updated? Yes, it is. Every minute, Harmony machine actually polls and updates the database telling like, hey, I'm still here. So you can see there's a column called last contact. It's the second column in the table, and that is updated every minute. And this is also what you see in your UI on your overview page, last contact from machines. You'll see it in seconds. If there's a machine which there has been no contact for more than a minute, we assume it's not available. Okay, any other questions? Great. Let's move on to the next one, which is Curio clusters architecture. This one is actually fairly straightforward. As you can see, Harmony is a system which kind of allows you to do a lot of things without actually trying to bog down in how those things are work internally. And this kind of gives us freedom to assign different kind of tasks and different kind of properties to different nodes, and that is very efficiently displayed here in the diagram. As you can see, there are compute nodes which do core rep, snap, unseal, and other SaaS even things that we want to do in future. Then we have proving nodes, which do window post, winning post, and hopefully PDP proving down the line. And then we have the network nodes, right? These nodes are your market nodes. Um, uh, they are basically the endpoints from where data or any other request enters the cluster, which is outside from your network, right? And as you can see with the new design, we have tried to only create one such endpoint, so there is less chances of security and other breaches, and hopefully you can monitor that with better tools. And it also allows you to not worry about open P2P ports and all of that things. So as you can see, most of this already exists, right? Some of it is research. One of them is chain. We don't have any plan to create our own chain node. And in fact, we are actively working with Forest to ensure that compatibility exists between Forest and Curio. It should right now, as far as I'm aware, it already works. And if you want to replace Curio nodes, replace Lotus as a chain node with Forest, please feel free to try it in KLMnet and reach out to me if anything doesn't work. I'll be more than happy to, work with you and Forest team to get things sorted. And yeah, as you can see, these are the different kind of nodes. Now, one of the good things about this design is that you can separate your storage, especially the long-term storage, as storage nodes from the cluster. I'll explain this to you in more details down the line. Okay, so one of the very important functions that we were actually trying to make sure works was multiple chain nodes, right? So imagine you have this huge cluster, you have HA, you have multiple things, everything is working fine, and suddenly the Lotus node you were connected to goes down and everything goes down. So that's not, that becomes a single point of failure. So that's not something that we wanted to have in our system. So one of the very I think this was maybe in June or July, a PR was raised to bring in some changes. And now basically Curio can talk to multiple Lotus nodes at once. And this doesn't work with Raft consensus or anything that was in Lotus Minor or in old Lotus, none of that. We are basically we kind of do this check every few seconds to all of the nodes. And if any of the nodes is not responding to us time, or if they are not in sync with other nodes, we mark that node as bad and we don't use it. Rest of the nodes can be used. Now, one of the important things here is winning post requires you to use the same node for all the calculations that are done during the duration of that task. So this feature has another feature within it built in, and which basically allows you to lock the node that you're going to talk to. Right? So you have 5 nodes, one of them is bad, you have remaining 4. If you were talking to node number 2 for winning post, you'll keep talking to node number 2 till the duration of winning post. And that is just specific to winning post as far as I'm aware of till now. I don't think F3 has any such requirements. So rest of the task and other things can easily use, alternatively any nodes. Now, next thing is GPU management. This was another point of contention when it came to Lotus Minor. If you gave it 4 GPUs, it might end up using all 4 GPUs for PC2 task, and it still takes the same amount of time. So that was not designed to. Okay, Julian, I'll come back to your question. So to basically have, so we basically wanted to kind of assign per GPU a task and let it focus on that particular task. So the answer we came up with is a bit of a more technical and weird thing, but in simple words, it's basically we have this small binary, right, which is kind of like Curio binary, but more stripped down version of it. And what it does is it starts an RPC server and it takes tasks. You basically tell it, hey, do this. And not like Harmony scheduler or anything. It is a more stripped down version. It does specifically, it's kind of like you call an API and it does all the calculations that API needs and gives you back the answer. That's the best way to describe it. So within this sub-binary, you'll see it running on your systems. You should see it's called FFI select or Curio FFI. You'll see these names when you monitor your GPU, and this is perfectly fine. It should keep running as long as Curio keeps running. And then within this, you'll see tasks being executed, like window post calculations from GPU or winning post calculations from GPU or PowerF from GPU and other things. So there is one more feature in FFI select, which kind of allows us to over provision GPU by certain factor. You decide what the factor is going to be. So let's say you have one GPU, but you want system to think you have two. You set this over provision factor to 2. And what happens is, let's say you have a GPU which has a lot of memory, right? And you're using it for post, and post doesn't really need a whole lot of memory. And the calculations are for very short durations, right? They're spikes. So what you really want to do here is, okay, let's make this system thing. We have 2 GPUs, even though physically we have 1 because we have enough memory, right? And our GPU is not engaged all the time. So you can basically do 2 window posts or 2 winning posts on the same GPU without actually messing up with how Harmony actually schedules the tasks. So this is one of the very important features. It's still experimental because not a lot of people have experimented it, but I do know a lot of you folks are using it, and it has been working properly. So it will probably move out of experimental phase soon. Let's see, we had a question in chat. Do we need keys imported on all the nodes? Yes, Julian, that is absolutely right. You need to have your keys imported on all the Lotus node. Otherwise, if you don't have the keys, there's a good chance we use one of those wallets and it's going to fail. Okay, let's move on to the next one. So let's talk about Curio setup and requirements, right? One of the very first requirement is Gigabyte. I know it's a bit of a learning curve to get used to Gigabyte. A lot of folks struggled with it, and I have worked with Gigabyte in past when I was part of Boost team. We explained them why we are picking up their product and why their community support needs to ramp up a little bit and help out Filecoin users. And they have delivered on all of it. There were some document issues that we got fixed, and they have also suggested a lot of changes in terms of how we are using tables and other things, performance issues and all of that in Boost, and it all worked out. And culmination of all of that work is now in Curio to speed things up. So Gigabyte in production, one of the very first things that I would say would be go with 3 nodes. Please do not go with a single node. And your Gigabyte cluster does not need to be reachable from outside. It just has to be reachable from within the cluster. Nothing else, right? Gigabyte provides 2 different APIs. One is your Postgres, right, which is used by HarmonyDB, which is the most important, the brain, right? And then the second one is SQL, Cassandra. That is used by indexing and purely for indexing purposes, nothing else. So if you have any questions or issues about Gigabyte, you can feel free to reach out to Gigabyte team on their Slack. They are aware of Filecoin users. You can let them know what you're doing and what kind of problems you're running in. You can even tag me in. I'm there in their channels. So you can tag me in if you need me there to reply anything. I'll be more than happy to work with you on that. So next one is hardware. Now, in terms of requirement, there has not been much change, right? Because at the end of the day, we are still doing those same tasks. We are still doing STR. We are still doing 3D. We are still doing encode or other things, right? So the basics of Filecoin hasn't changed. So the hardware requirement hasn't changed all that much either. But now you just need to be aware of the things that Gigabyte needs its own CPU and memory, and you should ensure that it always has enough CPU, memory, and NVMe storage. Now, NVMe storage is a must for Gigabyte to function fast. Otherwise, it's going to slow down your whole cluster altogether, right? And you're going to get timeouts, and nothing is going to work as it is expected to be. So it's very important that you have a solid Gigabyte infrastructure. Okay. Apart from that, and there's not much change in hardware. Back when you had like 4 GPUs, you were running, one Lotus Miner or Lotus Vogue for each of those GPUs. You don't have to do all of that in Curio. Another major requirement from Curio is it expects to be in charge of the whole hardware. So you can't run Curio and then run like 10 other processes on it. It expects to have access to all CPU, all memory, everything, and that's how it makes the decisions. So try to avoid sharing the resources too much. Like if you're going to use a very small process on it, that's okay. Or if you're not going to push Curio to do heavy tasks on it, that's okay. But you should always ensure that Curio has enough resources to do the task, so there's no OOM issues. Okay, next one is storage. I think a lot of folks are already familiar coming from Lotus Miner. You need two kinds of storage. One is the fast storage, which is used during sealing. And the other one is you can have slow disk, which is the permanent storage, right? That requirement hasn't changed. Any node which does any kind of sealing or PSpark or Snap pipeline, they need access to this storage. And of course, the store is straightforward, and that's where your data is permanently stored. For the seal type storage, the recommendation is NVMEs, of course. And for slow, it's up to you, but you should ensure that you have whatever your slow store is, it should be fast enough so you don't actually end up missing window post or winning post, right? Because at the end of the day, winning post and window post, they both need to go and read certain parts from the storage. Okay. Apart from that, next one is installation, which is actually a little bit better. Now we are shipping Debian packages for Curio. We ship one for CUDA based in architecture, and other one is OpenCL. So you can download either of them. We do not ship any packages for RC releases, and there are some releases where we intentionally do not ship packages. If you want packages for any specific release and they are not there, chances are it might be due to the release being unstable or being experimental in some nature. One of the biggest reason for this is we don't want somebody to accidentally run DNF update and end up going on a Curio version that they weren't ready for. One of the examples here is when we released Market, we didn't want people to accidentally upgrade their nodes. And that's where we stopped shipping packages for like 2 releases till everyone was aware of the things. So I doubt going forward, this is going to happen again. Apart from RCs, we are probably going to stick to ship all the releases as they come. Now, as soon as we release, packages are usually available within 24 hours. If they are not, please do reach out to me and I'll try to see what's going on. Okay, the second part of installation is building Curio from scratch. It has the same requirements basically for most parts, same as Lotus Miner. You need to have, if you're using NVIDIA GPUs, you need to have CUDA, you need to have GCC, you need to have certain other requirement packages, which are very well detailed in the documentation. And I have actually last week updated the installation page, removed a few things which were there for no reason. They were basically came there from legacy Miner, and have removed them, cleaned them up. If you're using CUDA, make sure to have certain environment variables set, like CUDA supraseal 1, to ensure that C2 times are faster. All of this is, again, documented in detail, telling you what to do and what not to do. There is also details about how to do this on Mac, but I doubt a lot of people are using Mac right now. So any questions till this point? Any issues that you are aware of in terms of installation or any other things? Okay, great. So next one is migration from Lotus Miner. I think at this point, anybody that I see in the meeting, I don't think there's anyone who hasn't already migrated. The migration is pretty simple, straightforward. You have, it's again very well documented, and you have one command on the Curio side, which is Curio and the guided setup. And then you just follow the instructions on screen. It just asks you, hey, where is your gigabyte? Give me the details. You give it the details. And then it asks you, hey, where's your Lotus miner? It's like, okay, or it will also even suggest you a few places where to look for Lotus miner. And once it finds a Lotus miner, it's going to just tell you, hey, shut down your Lotus miner, and it's going to go and open the database that Lotus miner has. It's going to fetch all the details which are related to sectors, right? All the metadata. So you know what a sector is in terms of like end to start, the whole thing, like it's all of its properties. Then it's going to go and fetch all the piece details, right, that a sector contains and all the properties there. And we're going to save all of that into the Curio database, which is HarmonyDB. And that's it. That's all we do. And we add the miner ID to the configuration layer, and then you can just start proving it. The next part, of course, is attaching the storage. Storage, the commands are pretty much same as Lotus Miner. You can quickly find them in the in the Curio documentation. So you just need to ensure that you attach these storages manually, one by one, on the correct nodes. Now, one of the very important things here is that storage need not, especially the permanent storage, need not be attached to all the nodes. So let's say for any reason before, when you were running Lotus Miner, Lotus Worker, you are attaching permanent storage directly to the worker which was doing post, right? That's not the case here. We don't have that requirement. As long as your storage is fast enough that we can read it on time, that's all that matters. You can run a Curio node on your storage servers and disable any kind of task, right? Do not allow any kind of task except move storage, and that's all you need. Now, whenever, let's say, a sector is sealed, instead of your sealing nodes moving the sectors, your node is going to go and pick it up and see, hey, this sealing node is finished doing sector XYZ. I'm going to go and fetch it and store it myself. The same thing is going to work in terms of indexing, in terms of IP&I ad generation. So there would be some load on your storage nodes, but if they are some very basic, if they're not like really basic hardware, you are probably not going to struggle. It's going to be completely okay to put the node, some of the load off to the storage nodes. So I think, John, this answers your requirement that you posted, that window post node need not be the storage nodes. Yeah, that's true now. Okay, so so the next part would be what kind of nodes, right? You're used to running a certain kind of, actually, we should quickly cover the new miner ID. So if you want to generate a new miner ID, you go and do the same thing, which is, again, Curio guided setup, same command that you use for migration. It actually has an option saying, I want to create a new miner ID. It will just ask you for some basic details like, who's going to be, which wallet is going to be the one that sends the message, which wallet is going to be the worker, which wallet is going to be owner, what kind of sector size you want, and that's it. It's going to send the message, and whenever it gets back whatever the ID it gets back, it's going to go and add that to the cluster, and you're good to go. There's no additional thing. You don't have to manually add it to cluster or anything. Now, one of the very important thing here is node type. Yeah, I think a lot of folks are already used to this concept, like dedicatedly saying this is going to be my PC1 node or SDR node, and this is going to be my PC2 node, and things like that. So till now, there was no way to tie all of the tasks on a single node in Curio. That was by design, but later we kind of noticed there was a bit of a flaw in our assumption. We shouldn't assume that nobody needs it. But now in the new RC, it's already part of the new RC, and you can actually bind your tree tasks, which are basically your PC2 and 3D tasks, to the same node which does the SDR. And POREP already is something that doesn't happen. POREP is basically your old C1 and C2, and they do not need your storage to be local. So POREP happens over the network, and it's completely fine. It doesn't need a whole lot of storage. It needs, I think it was like around 200 MB, if I'm right, or 256 MB, something like that. So it doesn't read a whole lot of data to generate the proof, and that's more than enough. So what you need to really care about in terms of sealing pipeline is STR, 3D, 3RC. Those are the only tasks you truly care about, right? That's where the requirement comes in, where the storage is going to be. So now there's an option where you can bind it. And if your storage, if your node can do STR, 3D, 3RC, it has the resources to do it, you can enable this option, and it's basically going to force a sector to go end-to-end on the same node, apart from the move storage. Because if you have a separate storage node, that's going to do the move storage for you. But that's inconsequential here. So any questions on that? Okay, great. So again, to quickly recap, storage nodes are something that were not part of LUTHR in general, but they are something that exists in Curio. You can have your storage servers become Curio nodes, and they don't do anything except move storage. That's one of the things, right? And then you have your post nodes, which do just winning post and window post. I highly recommend enabling winning post and window post on more than one node. And especially on winning post and window post, you can use GPU over provisioning factor. I recommend it to be 2, not more than that, because unless if something goes wrong, then you might miss the post altogether. So we don't want to do that. But then again, if you want to experiment and try to push the limit, it's entirely up to you. You can do that. You can set it to 3, 4, see where the system breaks and find the sweet spot depending on your hardware. Rest of the nodes are pretty much same, as I said, for sealing and proving and all of that. Sealing and snapping are same as before. One major change in Snapdeal is that we do not need the sealed copy to be local. We remotely read it, and we remotely read the data, and we encode it on the fly and save it locally on the disk. Okay, let's see. Okay, OC, your question is about boost migration, which we are going to cover later, not in this particular session, but next session. Okay, that was all in terms of presentation. Now, depending on the response that we get from you folks, and if there is interest to know more about how Curio works in specific tasks, how things happen beneath the hood, I can do all of those presentations. And I think it's very important for you folks to know about these things. It will help you run your system in the most efficient manner possible. So do let me know what you think about this and if you want to continue these sessions. If we do want to continue, this is something that I thought for the next session. We're going to cover the CLI, what is SP tool, why we need it. Then we will in detail try to figure out how storage configuration works and how storage CLI works. Then I'll tell you in detail what is vendor post and winning post and how they actually happen. What is the process behind them? I mean, some of you folks are aware of it, some of you folks are not aware of it, but I think it would be a really good session to understand how winning post and vendor post happen in general and specifically how they happen in Curio. And then, of course, we'll discuss one important aspect of running a Curio cluster, which is configuration layers. Now, after this, we can continue these sessions and cover more topics down the line. So do let me know what you think about this. I'm going to stop recording now. We will be publishing this recording hopefully on YouTube, and we will probably link this back to our documentation.